Hello, everyone. Can you guys hear me?
Yeah.
Nice. That's very nice. So let's wait a little bit for your other teammates. Let me check how many students we have. Yeah. Participants. So from what I see, there are 9 participants, right?
Yes, we have 8 people in the group.
Okay. Let me check. So there is somebody missing. In here we have 1, 2, 3. 1, 2, sorry. 1, 2, 3, 4, 5. So there are 5 people so far in the Zoom. Let me try to find your names, guys, okay? So there is Elias Gainulin. Are you here? Nope. Valerie Gerasimov.
I'm here.
Nice. Did I pronounce your name correctly?
Valery, yes, not Gerasimov, but Gerasimov.
Ah, Gerasimov. Nice. Thank you. Daniil Kolesnikov. Not here. Jalaluddin Kuldoshev.
Yeah, I'm here.
Nice. Alexei Potomkin.
I'm here.
Nice. Maxim Romanenko. Nope. Andrei Romanov.
I'm here.
Nice. Borja. Okay, Borja, I think he's not here, right?
Borja dropped the uni in the previous semester.
He dropped the university.
Yes.
Ah, okay, got you. Yeah, I know Borja, yeah. And then Timur Galimov. Good, he's here also. Okay, that's nice. So welcome everyone to this course. So the title of the course is Advanced Computer Vision, but the content, we will discuss it today together. So when we were discussing this course with what is it called? Education department or something like that. They told me that the software engineering course, like stream, does not have any machine learning courses. And this will be the first course on machine learning you will have. So we are trying to give you something like machine learning for software engineers, you can say. So we will not go very much in depth into every single algorithm, but the main goal would be to use these algorithms and build products that you guys can use in your everyday lives. So just to get to know you guys, can you please tell me through a small vote? Let me try if we can make a small poll, right? Can we make polls here? I think we cannot make polls in here, but we can try something online. Who of you guys already is familiar with PyTorch or Python? Sorry.
You mean Python, yeah?
Yes, Python. So who is already familiar with Python?
Which level do you expect of Python?
Just basic, for example, web programming, building some RESTful APIs. Nice. You can just use the raising your hand like this thingy. It's very useful. So building, for example, RESTful APIs through something like Flask or yeah, something like that. Who is already familiar with these kinds of Python stuff? Nice. So just from a show of hand, I can see that mostly everybody is already somewhat familiar with it. Nice. Can you describe to me what else do you guys know in Python? So what did you do with Python?
REST API, for example, on Django and Flask and FastAPI.
Nice. That's very nice. That's very nice. Now let's go a little bit to machine learning. So who's already familiar with the basic concepts of machine learning? So something like linear regression, something like decision trees, support vector machines, clustering. Nice, that's nice. So can you tell me, Valerie, what do you know about machine learning so far?
Well, classification sounds familiar for me.
Classification.
Uh,
Yes. Okay, gotcha, gotcha. Anyone else has some experience with machine learning in the past?
A bit by using the just SVM and
SVM?
CNN and Kamins. And I passed some courses in machine learning, but that's all.
Nice, nice. Okay, got you. Now let me ask a little bit more questions about, well, this one is going to be easy. Do you guys already know PyTorch? Probably no one, right? Okay, so far nobody. Let's ask the final question. Do you guys, are you already familiar with web development and mobile development? So mainly from the front end side. Nice, 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 nice. Good. So can you just go around quickly, describe to me what you have already done and what you're familiar with doing?
I developed some projects in Vue.js.
Vue.js. Okay, got you.
Yeah.
Got you. Did you like do it with Laravel in the backend?
No, it's .NET.
Okay, got you, got you, got you. I remember working with Vue.js like a couple of years ago. It was very nice. That's a very good library or framework. Yeah. Anyone else?
Basics of HTML, CSS, JS, and other frameworks such Angular, React, and Vue.
Nice. AngularJS or Angular. Yeah, it's good. Well, what else? Anyone else? Maybe someone from mobile development?
React Native, some basics.
Nice. React Native is also very nice. Anyone else? Does anyone else have any experience in mobile? Probably no one, huh? Got you, got you. So what are the programming languages that you usually use? So is it Java, is it C++ or C#? What is it? Or PHP maybe?
I use mainly C# and JS.
C# and JavaScript, nice.
Me too.
Nice. Anyone else?
Java, Python, and Scala.
Java, JavaScript, and PHP. Makes sense. Good.
No, Java, Python, Scala.
Ah, yes, yes, I know. I'm reading the comments.
Oh, okay.
Nice in the chat. That's good. That's good. So you're already familiar with Scala. Did you do some stuff on like big data and parallelism and stuff like that?
Yes.
Nice. That's good. That's very nice. Хорошо. Let's start with a small introduction on myself and just the course. And then we will start the first lecture, right? Let's go first. Is everybody in Moodle and everything working well on Moodle?
Yes.
Nice, nice. Okay, gotcha. Let me share the screen. So the official title of the course is Advanced Computer Vision, and that's because like of some legal issues, we can't really propose different electives for software engineers right now for the summer thingy compared to the other spring semesters and stuff like that. So for some legal reasons, we need to keep the name as Advanced Computer Vision, but the real course, his name is Machine Learning for Software Engineers. My name is Bikush Imad. You can just call me Imad directly. And well, I'm pretty active on always online on Telegram. So just send me a message whenever you want, and I'll probably reply very fast, right? A small introduction of myself. I did a bachelor's in computer science in Algeria. Then I did my master's in data science in Innopolis. And currently I'm doing my PhD in AI in Sorbonne University in France, Paris. Work experience, I've worked with Provectus for around 2 years, and I worked in 2 of the Innopolis research labs, mainly for the machine learning lab and the industrial artificial intelligence center in Innopolis University. My main research interests are computer vision, domain adaptation. So domain adaptation is a field, it's a field of, it's a subfield of transfer learning. Maybe some of you are not already familiar with what transfer learning is. In simpler terms, when you have a very difficult machine learning task and you don't have enough data to train a strong model on this task, usually what we do is we try to find some big data set somewhere else, use that to train the model first, and then we finish the training on our data set, and this hopefully will improve the results on your own data set. So this is what domain adaptation is. Domain adaptation tries to leverage multiple data sets to improve the performances on whatever data set you're targeting. So for example, if you're trying to work on a data set of, what are they called? Signs, you know, those like language of the people who do not speak. I forgot, sign language, yeah. So if you're trying to identify the characters of sign language, for example, and maybe your data set has only like 200 images, this is not enough to build a very strong computer vision model. So what you can do is bring another data set that is not relevant for sign language, say a data set for cats and dogs, but you have lots of images there. Train your model on that large data set, and then fine tune it. That's how we call it. Fine tune that model on your sign language data set with very small amount of labels. And the last part would be knowledge graphs. So knowledge graphs is a, well, kind of a data set. You can think of it as a database format where it's not like tabular data set, but concepts are related inside of a graph. So it's basically, you can think of it as having a concept such as the Mona Lisa painting related to other concepts such as Italy, such as Leonardo da Vinci, the current location of the Mona Lisa. All of this information is stored inside a very large graph, and extracting information from such graphs is one of the fields of research that I'm working in currently. So if you guys want to maybe have or have any ideas to do research in these 3 fields, you can contact me and we can work on this together. Now for contacting, again, you can just call me through Telegram. Most of the time I can reply very easily. Send me an email. So this is my Innopolis email, or you're already inside the, what is it called? The Telegram channel, right? A Telegram group. Now for the grading, mainly your grade will be on group projects. So there will be 3 group projects in total. They will be kind of relatively easy if you're already familiar with what is it called, web development and stuff like that. So the goal, as I said, is to get you guys to train and deploy as many models as possible. So when I was doing this course for machine learning engineers, their goal was to really train and tune these models to perfection and understand the theory behind every single model. Now, your goal as software engineers would be to deploy the models that a data scientist would give you, right? So basically, in an environment, we usually have somebody who's a data scientist. He has no idea what the JavaScript is, or he doesn't really know how to use Flask or RESTful APIs and stuff like this. So usually your job as a software engineer would be to interact with these data scientists, speak kind of their terminology. So you need to understand the words that they use. You need to understand when they say training data set, validation data set, testing data set. So all of these terminologies, you should be able to understand them and later take their trained models and build projects around these trained models. So again, the goal of this course is to give you kind of an idea, what is machine learning? How can you really do this intelligence part, right? Using just code. And then would be just to quickly understand this model does this, this, and this. This is how you can simply train this model. Go ahead and use these models in real life. So this is the purpose of the 3 group projects. So basically, again, using machine learning to build a useful product. I think most of you guys will go for the web. If somebody also is interested in mobile, you can go ahead and build some products for the mobile, right? And then the final 25% of the grade would be on quizzes. So usually we would have around 2 or 4 quizzes before the lectures. So preferably next week, we'll already start with our first quiz, and we will try to distribute these quizzes between the different lectures and the different weeks, okay? Let's just verify that everything is done. Nice, nice, nice. Okay. So I think this is a good introduction so far. Do you guys have any questions? Yeah, go ahead, Andre.
What deadlines we will have for each group project?
That's nice, that's nice. So from what I see in this, let me check. The planning, we have till the 23rd of the 7th month, right? So basically we are together for 2 months, right?
Yes.
Nice. So the first project, I would probably give it to you guys next week. And you would have 2 weeks to finish it. After that, I will give you the second project. You will have 3 weeks to finish it. And then I will give you the final project and you will have 3 weeks probably to finish it. Sounds nice?
Yep.
хорошо. Again, if you guys have any like project, not projects, like if you have some exams or something like that, you can just tell me and we can try our best to push the quizzes of this course away from the periods of the where you guys will be doing exams in other courses. And same thing for the projects, of course. Are you studying other courses or is it just this course and another elective?
We have 2 another courses and industrial project.
Oh, okay, got you. So industrial project. Yeah, yeah.
Industrial project and 2 another courses.
хорошо. Nice, that's nice. So now before we go to the first lecture, can you guys start telling me what are you expecting to learn from this course? So what do you want to learn from this course? Go ahead, go ahead.
Maybe basics of machine learning,
Mhm.
maybe training the model,
Mhm.
analyzing data maybe, and predictions maybe.
Uh-huh. Can someone else give some opinions? Maybe object detection, stuff like that. Does it interest you?
Yes.
Nice, nice. So I think you can check with your industrial projects. Usually, I think the recruitment would be, you would be working in the same company that you did your, what is it called, industrial project in. So usually that's like the easiest way to get hired in Innopolis. For that, I would recommend just go to them and see what are the different kind of jobs that they want. And we can do them together here. So basically, you can go and see, maybe they have like a data science team who's working on some object detection tasks, and you would like to be able to understand what is object detection and speak with that team. Later on, you will most likely be, so usually what we have is like a group of data scientists and a software engineer as the team lead. So this usually works much better than having a data scientist as the team lead, because usually data scientists are not very good at software engineering. So in that case, mostly you will need at least to understand what your data scientists are doing and speak their language, right? So basically there are different types of tasks that you can do in in machine learning. So you should kind of try to understand what you will be doing in the future, and we can focus on that in this course, right? So it's basically just a preparation for what you will be doing in the future. For today's lecture, what I prepared is image classification. And for that, I want to first go through some of the old machine learning models and explain to you guys how do these models work, and then progress to start speaking about computer vision, not computer vision, yes, about computer vision and image detection, neural networks, and all of these concepts. Okay?
Yeah.
Хорошо, let's start. Так. Oh, I didn't share the screen. Share screen. Do you have any questions so far?
I think we
Not
have
yet.
no question.
Хорошо, nice. So again, the goal of this, let me try like this.
Hear me better like this? You mean
Some noise behind you.
There's some noise behind me. Okay, I think I should just go back with the. Like this, you can still hear me very well?
Yes.
Yes, better.
Nice. Okay, so the goal of this lecture is to speak about image classifications using CNNs. Probably this lecture we might spend on it 2 or just probably 2 weeks, yeah. It will have 2 labs. So basically today we will start our first lab, and then the next week we will do the second lab. The learning outcomes of the lecture are, first we will be speaking about normal neural networks. And in order to speak about neural networks, we will be speaking about some of the older models, such as linear regression, logistic regression, and decision trees. And then we will speak about what convolutional neural networks are, why are they different from normal neural networks, and then we'll just give you some tips on how to train your neural networks, okay? Let's start. The first part, I would like to ask you some questions. So can somebody tell me what's the difference between these 2 terms, regression and classification? Do you have any idea about what's regression and what's classification? Have you heard about them?
Well, I think I can.
Yes, go ahead.
Classification, when we have some objects and labels, and we should assign a label, a single label to a single object, or maybe
Okay.
other variations, but this is most basic. At regression, we have a set of objects, and we should assign some number, maybe double, but it's not labels.
Very well, very, very, very well. So again, as your friend just described, regression is a task of machine learning that works on predicting digits. So for example, we try to predict the price of a house based on the features of the house. So for example, you have a data set that says this house contains this amount of square meters. This is the location of the house. This is the distance from the house to the closest metro station. And all of these features, you use them to predict what should be the best price for this house. So the price, again, is a digit. It's a number. Another example would be to predict the age of a person. So the age of a person, he is 25, he's 33. And we can take, for example, the image of a person and try to predict his age, right? And the last one would be to predict the temperature of, for example, the temperature of a room based on some, I don't know, some feature, like some heat map. You take like a heat picture of a place and you try to predict its temperature, right? So basically, regardless of what the input is, the goal of regression is to do or to predict a digit or a number. On the other hand, there is classification, and the goal of classification is to predict a class, right? So we're trying to classify different objects. So for example, we have a car, and we're trying to predict what is the type of this car. So is it a Lamborghini? Is it a Ferrari? Is it a BMW? So we have different classes, and we're trying to predict one of these classes. These classes are not continuous space. So the difference between classification and regression is this continuous space. In regression, the space of predictions is very continuous. So you can be like $300 or $300.02, right? Whereas, for example, for BMW and for cars, there's no such thing as something in between. So it's either BMW or it's a Ferrari, right? So there's no line that you can walk through and all the values are valid. In this case, we are speaking about categorical values. And in this case, we're speaking about continuous values. We're trying to predict continuous values. And again, regardless of the input type, the classification regression difference is only in the output type. So another type of classification would be to predict or to read characters from a screen. So basically, it's very popular nowadays, optical character recognition. So for example, you take a picture of some phone number, and what we try to do is we extract the numbers from that picture. So basically we have number 1, number 2, number 3, number 4, number 5. So these are different classes, right? So for us, the concept number 1 represent a class. It doesn't represent a double number 1.0. Exactly. So why do we do this? Because why do we represent it as a class and not as a number? We have it in the following. 3.14. If I'm trying to predict 3.14, then I'm trying to predict something for regression, right? So let's say it's $3.14. Now, if I tell you that I want you to read the bill of some, what is it called, of some product and extract the price, what you will be doing is you will be extracting every single one of these numbers. You will not be looking at 3.14 as a digit as it is. So for example, as a double, you will be extracting it as 3.1 and 4. So what we are doing here, we are treating this double concept as a set or a sequence of classes. This is much better for performances of machine learning models and usually provides much better results. Do you guys need me to explain this in different ways, or do you already understand the difference between predicting a number such as the price and predicting the class of a number such as class 1, class 2, class 3? You don't have any questions?
Maybe a little explanation need.
Хорошо. Let's do it again. For classification, let's take this example. We have the example of classifying the type of an animal. So for example, we take a picture of the footsteps of that animal, and we try to predict what is this animal that walked through here. So is it the dog? Is it a snake? Is it a horse? Based on just the footstep of that image, of that animal, right? So basically the input is an image, the output is a class. So it's a category, right? Either dog, a horse, a cat. You cannot really make some order between cat and dog and horse. These are very completely separate concepts that cannot be related together inside one line, or cannot be represented inside one line, right? Inside a continuous space. Whereas here, for example, for the price, we can easily represent the price as a line, right? So this is the price, this is the line for the price, and your prediction can be anywhere on this line. So it can be, for example, 0, can be 0.1, can be 15, it can be 16, it can be -12. So this is what I say, or what we mean with a continuous line, right? So you can see that there is a very big difference between predicting a value like this that can take any possible output that can be made. So for example, here we have 1.3, 4, 5, 6, and 7, right? So this is one possible output that the model can give you. It is a valid output. This is called regression. On classification, the model will only give you something like this: cat, dog. You cannot really build cat and dog on a line and say that every point on this line is an acceptable answer from your model. So this is the difference between classification and regression. Classification works on classes like this, whereas regression works on double values or float values. It tries to predict such things, right? So 0 point something. Did you get the difference now?
Yes.
Nice. Now, let's go back to the MNIST dataset, or the detection of the category of a number. So for example, I give you a dataset of pictures of these numbers. These numbers are all integer numbers that range from 0 to 9. If I tell you to build a model that can predict the type of every single image, or predict the number inside every single image, would you tell me it's a classification task or a regression task? So let's say this is the image that I'm going to give you.
Classification.
Nice. Why so?
Because when we use, in order to use regression, we should we should have history numbers, I think, and based on that history, we can predict future numbers. Here we just recognize the picture and just read the picture.
Yes and no. So you are very correct when you said it's classification task. Why is it a classification task? Because, as I said, the values, the possible values that we can have are only 1, 2, 3, 4, 5, 6, 7, 8, and 9. We cannot have a value of 1.3 in the output of the model. So the 1.3 is not acceptable answer from the model. This is why we cannot put our predictions on a line and say this is 1, 2, 3, 4, 5, 6, 7, and 8. So all of these values in here on this line are not acceptable from our model, meaning the task cannot be a regression task. Did you get the difference?
Yeah, you mean we have exact class, and the value should be included in that class. You mean? Yeah?
Exactly. Yep. So here, what I'm saying is the possible answers that you can have are limited. So you do not have this continuous line where you can say any number you want, and that would be an answer, right? So if I say that the price is 300.12, that's an answer. But if I tell you that on here, on an image of a digit, if I tell you that this is 737.12, this is not an acceptable answer. What I want is what is the class of this image. The class can be anything. It can be like, for example, the type of the dog, right? Is it a Chihuahua or is it a bulldog? Or it can be a number. So this is a very important distinction that you guys need to make between regression and classification. We will speak about this. We will see more about the regression and classification in the lab, and probably we'll understand a bit better these concepts when we see them in action, right? The first model we will speak about is called linear regression. So linear regression is one method of regression, as its name suggests. And what it tries to do is predict a continuous value based on some input values. So for example, in this case, we have the weight of a person, and we're trying to use that to predict the height of a person. So let's say we have a small data set of the following. So let's say we have the following data set, right? The weight in kilograms. Sorry, let's do text like this. So weights in kilograms. This is the input, and the output is the height in centimeters. Can you tell me, is this a classification or regression?
Regression.
Regression. And if I said I don't want the height in centimeters, I want to see if the person is tall, short, or medium. So what I want is I want to give you the weights, and you tell me if the person belongs to any of these classes. So I'm not looking for the height. I'm looking to understand whether the person belongs to these classes. Is this classification or regression?
Classification.
Nice. So even though we are speaking about the same concept, which is height, in this example, we are speaking about it in numbers, in centimeters, right? Whereas in this example, we're speaking about it as classes. We're speaking about it, is this person too tall, or is this person short? Or is this person a medium? We don't say this person is 160 centimeters. We don't say that. Only thing we say, does he belong to any of these classes? That's it. Now let's continue.
May I summarize the difference between regressions?
Yeah, go ahead. Yeah.
Yeah, as I understand, the classification and regression all about precision, but regression about quantity prediction, and classification, it's about label prediction. Right?
Perfect. Yep. So for classification, we're trying to predict labels or concepts or classes or categories. You can use all of these terms. We're trying to predict a concept, whether the object belongs to a concept. And in regression, we're trying to predict a continuous number on this object. So for example, which we have a person who is 80 kilograms, and we're trying to predict what is his height. The height in centimeters is a continuous value. Let's say here we have somebody who is 60, or let's say 170 centimeters. 100. 50. So this is our data set. It maps the weights into the heights. Can you tell me, do you know of a method or a simple trick to convert this into this? So this is the goal, right? We're trying to give you as inputs the weights of a person, 70 kilograms, and I ask you, what is his height? So this is the task that you are given as a data scientist. Can you think of a method to do this?
Do we have any set of classes?
Can you repeat this?
Do we have any set of classes for the pairs of weights and height? Only this table.
This table, yep, that's it. You have 80 kilograms, gives you 107, 80, 60 kilograms gives you this, 100 kilograms give you this.
We can get regression coefficients and somehow to predict this value.
Nice. What is regression coefficients?
Linear regression is this straight line. It's golden, maybe average, maybe all of.
Got you.
Maybe.
Got you. So let's say we have the following. Can we just build a simple if statement? If weights equals 80, then we return 180. If weights equals 60, we return this. If weights equals 100, we return this. Is this acceptable?
Yes, why not?
What is the problem with this method?
We cannot predict other inputs.
Exactly. So if we have a new input, our model will not be working. So let's try to find, can somebody give me a simple physics formula? Something very simple. I don't know, I'm not good with physics.
We can add 100 to the weight and get height in centimeters.
That's a very, very smart idea.
Approximation.
So height equals kilograms weight plus 100. And this is a good approximation, right? It makes some errors, but it's okay.
We don't know the good or bad, but it's one of the approximations that we can use.
Yeah, it's okay. So it's doable, right? Another one would say it's like this. It's 3 times the weight minus 40 for some reason. Why not? This is a acceptable method that can convert, or it's an acceptable formula that can convert any weight into the height. So if I give you this formula, can you easily answer this question?
Yeah.
Nice. So let's see. 3 times 70 minus 40, how much is that?
$170.
This is too much math for me. 3 times 70 equals 201 minus 40 equals 170. Yes, centimeters. Yes. So now you answered the question. Now the real question is, how can I get this formula, right? So we saw that this formula is very useful for answering questions like this. Can I predict the height of a person based on his weight? And we saw that we can if we represent it in this formula. So the real goal here is to understand how can we learn this 3 and minus 40, for example. How can we learn these concepts? And this is where linear regression comes in place. So linear regression, what it tries to do is estimate the y equals a times x plus b. We're trying to estimate this a and b to find the best values of A and B that make the smallest mistakes, right? So we take our table from earlier, like this. Ta-ta, ta-ta. So here we have, for example, 80. Here we have 180. Here we have 60. And here we have 170. So what we're trying to do is we're trying to find the best values for A and B that once we plug them into this table, the difference between this 180 and the output of this formula should be very small. So we're trying to find these coefficients, A and B, that minimize the error in the predictions, right? So we're trying to predict as perfectly as possible, meaning we're trying to minimize the difference between the real value and the predicted value. Is this understandable?
Yes.
Nice. Now, there are two methods for solving this problem. So there is one which is completely mathematical. So basically, some very smart person in mathematics just went ahead and built the derivation of this. So let's say this is the predicted y, let's say predicted output minus, okay, let's see, predicted output minus y. And then what he said. So he just built the derivation of this one with regards to x. And then after some simplification of these formulas, he actually found that A should be equal to some function of x, and B should be equal to also some function of x, and that's it. So basically from the, x and y. Basically, after some mathematical formulas, you can just go ahead and plug this function directly in, and it will calculate for you your A and B, and you will have the best possible representation that gives you this. Predicted value equals A times X plus B. So what is this A plus times X plus B represent in reality? So it's the following. So we're trying to build a mapping between the weights and the heights using a line. So you can see here, this is the line of our data set. This is the predicted values. And they're not very much different, right? So here we have a small difference. Say this is 150 and this was like 153. So this is good. Again, small difference. Here is a large difference, another large difference. This was perfectly predicted. Some errors in the predictions, some errors, and some errors. So this is nice, right? So the model is doing something. It's not very bad and it's not very good. So there is some error, but it's doing its best. Now let's speak about the error itself. Can somebody tell me what metric should we use to evaluate whether the model is doing good or bad?
R-square?
That's too advanced, right? Let's build up to R-squared, right? Let's start from something very trivial.
The square differences.
Why
Root
square?
of square differences.
Y square, maybe module,
Why
absolute
module?
value.
Why module? So the
What do we
simplest
do?
one.
Just
What is it?
differences between predicted and
Exactly,
real
right?
value.
This is your error. So for example, here I predicted 170. Here I predicted 250. This difference between these two values is my error. That's nice, right? Now, why did your friends describe or propose to use the squared or the absolute value? Can somebody explain to me why?
Not to get the negative value, maybe. We use squares.
Nice. But why are negative values bad for us?
Because Plus 15 and minus 15 would give us 0, but
Exactly. So here, if we do this difference, it will be a negative number, right? So for example, minus 15, as your friend said. And then for the others, let's say minus 2, minus 3, minus 4. When we do the difference in this case, it will be a positive number. So it will be plus 20, for example, right? This combination of negative error and positive error will in the end give you equals 0. So if you calculate the error of the model in total, you will see that the model makes no errors. The model is 0 error, gives you 0 error if we're just using this difference between predicted y minus the real y. Sometimes it's positive, sometimes it's negative. If we make the sum on all the values of your data set, some of these negative values and these positive values will like take off each other's, and we end up with a 0 loss. So this is not very useful for interpreting the performances of the model. This is why what we do is we convert, for example, let's say, all of these numbers into positive numbers. Plus 2, plus 3, plus 4, plus 20. Like this, you have a better understanding of what is the error that the model is giving you, right? So just by applying the absolute value on the loss functions, we can get better estimations of the results. Can somebody tell me why is the absolute value not a good metric? And why do we use, as your friends described, the squared error instead of the absolute error? Can somebody think of it? Let's give you a small question.
How does yellow value helps to us?
Can you repeat, please?
How does yellow value helps to us?
How does what?
Yellow value helps to us.
The loss value.
Yellow value.
Can you type it? I couldn't really understand.
He means, I think, error value.
Yes, the error value. How is the error value useful for us? In two things. First, evaluation of the model's performances. Two, how does the error value help to us? That's very nice. So remember when I said earlier, how do we predict the values of A and B? As I said, there was a very smart person who used this function, py minus y, and then tried to derivate this loss until he found the best values of A and B. Now, if we keep the loss like this, as we saw, the positive values will influence the negative values and the calculations will disappear. So what we just said is we apply the absolute value to this one. And then our mathematical friend, he will come here and do the derivations of his functions and find the best values for A and B. But if he uses the absolute value, our mathematician friend will fall into a small problem. Let's see what is this problem. Can somebody tell me what is the derivation of x squared?
2x.
2x.
2x, that's a good answer. Can somebody tell me what's the derivation of absolute of x?
Well, on most of the positive values, it's x. I don't know, it's 1.
And minus 1.
Or on the negative values.
You see, so this plus 1 minus 1 is the reason we don't use absolute value, because absolute value does not have one stable, what is it called? Help me out. One stable derivative, right? So in the positive values, absolute has a plus 1 for its derivation, and in the negative, it has a minus 1 for its derivation, right? So if we try to just draw here how the derivative of absolute value works. So there you go. And then there you go. One very bad thing about this function is it is not a continuous function. But for 2x, let me put 2x here. Here's 2x. It's a continuous function. Now, our mathematician friend likes continuous functions because they can help him simplify the math. This is why we use the, what is it called? The squared error instead of the absolute error, because using the squared error, we can easily find the derivatives and simplify our math to find first the values for A and B. Did you guys understand this?
Yes.
Хорошо. So again, our first initial idea was to just use the difference as error. Then we saw that because of the positives and negatives, we get some problem and the positives neglect the negative and we have a zero error, which is bad. So we decided to use the absolute error, right? And then we saw that the absolute error is not easily differentiable. So we decided to use, instead of the absolute error, we use the squared error. And that's it. So basically, this is the final error. So it's the sum of all data predicted y minus the real y squared. And this is it. This is your final error, right? Difference squared, we sum it on all of these different instances. And this is your way of evaluating whether your model is doing good or doing bad. We will see this better in the next lectures, and we will see it better in the lab. But for now, remember that we have our good idea or our method for calculating,
May I ask, please?
Yes,
The last formula was about the sum of squares, yes?
Yes, exactly. So it's the sum of squared errors.
Okay, thank you. And may I ask the second question?
Yes.
When we try to get absolute value, can we define the slope as a zero for our function?
Yes, you
regression.
can put any value for the model as long as it gives you good results.
Okay, thank you.
You're welcome. Now, just a small, I forgot to ask you this, guys, before. How do you like to do your lecture notes? How do you like to save lecture notes, to write lecture notes?
What do you mean?
Do you guys maybe like to write them manually? Or some of you like to write, for example, lecture notes on Google Docs or maybe on Notion, something like that? The lecture notes, how do you revise for classes?
We see recording our lectures again.
Okay, got you. So seeing the recording of the lecture again is too much time, right? It will consume a lot of time for you guys. So what I prefer we would do is to write the lecture notes together. Let me share with you an example. Share screen. So basically what we will be doing is simple. We will create this shared Google Docs. And as I am doing the presentation, I will be using my other laptop to write important information inside this Google Docs. And like this, later on, of course, you will also have access to this Google Docs. You can write on the Google Docs, you can put your questions and write your the answers that I give you guys here. This way, everybody will have access to some sort of lecture notes that they can use to quickly revise the content of the lecture without having to forget anything, right? To risk anything. Should we do this, or you guys don't like it?
Oh, we didn't do it.
Yeah, exactly. In what is it called? When I was studying in Russia, in Innopolis, we never did this idea. But when I came here to France, actually everybody is doing this. So I thought that it's a good idea to incorporate it in your lectures. Would you guys like to try this, or maybe just skip it and everybody writes their own lecture notes? Go ahead. Just give your thoughts, guys. Let me stop sharing and just vote using this raise hand. If you approve on it, raise your hand. If you don't like it, then just don't raise your hand. Nice. Хорошо, we have 4 already who raised their hand. That's nice. I personally find it very interesting to like bring the student inside the lecture. So basically this will help you guys, what is it called? Write your own lecture notes and share this information together. And when you are writing the lecture, you understand the lecture better. So this is what I found through studying here in Paris, right? So let's say the first lecture on image classification. Let me share this on the Zoom channel. Anybody can be an editor. There you go. I will also put it on your Telegram. Nice. And we can write it together. Nice.
Using your practice, is it effective way to note lectures?
Yes, it was very useful for us to learn about like practical concepts, right? So especially when you have a small group like this, it's much better to do it together, right? So previously, when I was teaching this course for the others, for data scientists, I had a group of over 40 students in the same group. So that was very difficult to handle this method. But in your case, we are just 8 people. So it's very easy to collaborate together and work together. Let's write here, for example, machine learning for software engineers. Nice. So let's do it together here right now. What is the difference between classification and regression? Can somebody put the description of classification? Another one puts the description of regression, and another one will put examples of classification, and another one will put examples of regression. Go ahead, go ahead. Examples here. Prediction of a label, of labels. Perfect. Can you give me different synonyms for the word labels, right? So like in front, just put inside parentheses, give different synonyms for the word labels, like categories, classes, something like that. Go ahead. Nice. Exactly, very important when you spoke about the as input, right? Give me different input types that you can have. In here. So as input for classification, can you take images for input or classification? Nice. I hope that everybody is participating in this. So try to, everyone, the more you write in this document, the harder it will be for you to forget about the concepts that you're learning. So this will be a very important information, like method for you guys to just keep this knowledge for you for a very long term, right? Nice. So images, text vectors, numbers, anything that can be fed into the model is being fed to the model for classification or for regression. So the input does not define whether it's classification or regression. It is only the output that defines whether it's classification or regression. Nice. So classification, we're trying to predict labels. We're trying to predict quantities or continuous values, right? Let's write it in the thingy. Continuous values, right? As output, it must be floats, right? Nice, very nice. As input, again, anything you want. Can I put an image as input for regression? Yes, I can put anything as input for both classification and for regression. So the input does not affect whether it's classification or regression. Nice. Novels, genres as outputs. What is a novel? Novel. You mean like those books, right? And we're trying to predict the genre of the book. Nice. We can try cats versus dogs, right? This is another classification. The type of car, it's another type of classification, right? Now let's go room number, location, age. So all of these things that can be represented as, for example, salary based on studies, right? Nice. Now the next step, which is linear regression. Nice, let's start. Tell me what you guys understand about linear regression. First, what it does, how it does it, how does it learn, and how do we evaluate it? Go ahead. Everybody should go and answer one of these questions. Nice. Nice. What do you mean the word future? Nice. That's very nice. Okay, got you. Let's call it the target value, right? So something that we want to understand. Good. So this is our target. This is our prediction, the thing that we want to understand or the thing that we want to predict. Predicts the value. Is it like classification or regression? It's regression. Very nice. So let's say it predicts a float value, a target float value. Nice. Good, very well. So it's a regression. How does it do that? So by using some mathematical approximation, by building a linear function. Very well. Can you write the linear function formulation? Oh, very nice, very nice. You found something on the internet. This is also very useful. Nice. Y equals a x plus b. Now, we need to find, nice, a and b. Perfect. So if I ask you a small question, once you finish the training of your linear regression, what is the model that you will be storing? If you want to save this model after you finish training it and you want to use it in another location, what is the model that you will be transporting? So what's the model that you will transport? You can answer me on audio. It's better, right? If go ahead.
You mean it's trained? You mean the name of the trained model?
We trained the model. Now
Yeah.
we want to use this model in our application, right? How do we
Yeah.
transfer this trained model to the application? Do I send the whole training data set? Should I send
No,
some...
algorithm maybe.
What is the algorithm, right?
We during the training we choose best algorithm which predicts the data most in proper way, maybe with most less errors. Yeah.
But in this case, in the case of linear regression, what is the model that you have that you have learned?
Coefficients.
It's the coefficients, exactly. So if you want to transfer this model from a location to another, what you need to do is just copy this A and B and send it to the other place. That's it. Now you have transferred your model. So you see that linear regression is very simple. You're just taking with you a small amount of float values. That's it. So for example, A and B. If you have, let's say you have AX plus A2. So A1, X1, A2, X2. So for example, say that you have, how do we put this up? Yes, subscript, right? 1.
Maybe someone will share the document.
You don't have access to the document? I shared it on.
Yeah, I have an access.
You mean share the video of the document? Here you go. Like this?
Yeah, thank you.
You're welcome. Da-da. Nice. Nice. What we need to do is to find A and B. How does it learn? Using historical data. Do not use the term historical data like this, because usually the term historical data is used for other types of models called as recurrent models. So in our case, it's true that the data set is old, right? So we're training on some old data and making the predictions on some new data. That's true. But we don't use the word historical in the case of machine learning very easily, right? So the word historical usually has a very specific meaning. So let's try to not use the term historical, but let's say using training data, right? Pre-annotated. Annotated, right? This is much more accurate term for saying the same thing as historical, as what you wanted to express. That we already have, we try to get coefficients to make smaller errors on average. Also make attempts to find relationships for input data. Less is, it is then better. Nice. So again, how do we evaluate it? Let's put this first, let's put the logic, right? So first we have the difference. Can somebody tell me why the difference is bad? And then we said we use the absolute error. Can somebody tell me why absolute error is bad? And then we said the squared error. And then somebody explained to me why squared error is good. Why is the difference bad as a metric? Mm-hmm. Can you guys still hear me?
Yes.
Go ahead. Somebody tries to write or explain why is a difference bad as a metric? Mm-hmm. There are no right and wrong answers, guys. We're writing it together. So please try your best to express. So the goal of this is for me to understand whether you guys have understood well or not. So it's kind of a method for evaluation of what you have already learned, right? So just to make sure that everybody understands these concepts, please try to participate in the writing as much as possible. This way I can help you like fix the errors as you go. So you don't need to like stay with the wrong information. Mm-hmm. What does this possibility of negative values mean? Like there's a possibility of negative values which implicate like what happens when you have negative values and positive values.
I mean,
No,
we
just
get
write it.
maybe. Okay.
Yeah, go ahead. Somebody tries to write it in the document. This way, later on, when you're trying to revise, you all have seen how this document was written, right? So everybody knows exactly where the information is. If you want to find something, usually your brain will directly send you there. Mm-hmm. Nice. Nice. For absolute error, it removes negative values, right? And can be used for evaluation. It cannot be used for predicting A and B because it is not easily derivable. Whereas squared error okay. Nice. Whereas squared error, it's much better for the following reasons. It removes negative values and can be used for evaluation and can be used for predicting A and B because it is easily derivable. Nice. Now let's speak about the next type of models, which is logistic regression. It's very simply, it's a very simple model. It's very closely related to linear regression. We will speak about it in very simple terms and then see the difference between these things in the lab, right? So the goal of logistic regression in reality, it's to predict, no, sorry, this was an error. Type of height of a person using his weight. Meaning the goal of this is to predict whether a person is tall or short. So this is what logistic regression does. So we're trying to predict, is he a tall person or a short person based on his, let's say, weight, right? So basically what we have is a simple data set of the following. Yep. So basically what we have is a simple data set like this. Text, let's say kilograms weight, and here tall or not. Let's say here is 80 kilograms and he is tall. Let's say here we have 70 kilograms, he is also tall. We have here 50 kilograms and he is short. Right, so this is the data set that we have now. And we're trying to use this 80 kilograms to predict one of the two classes that we have, which is either tall or short. One person said, why not use linear regression, right? So it worked before, why not use it right now? So what he did is simple. He went to this class tall and represented it as the number 1.0. And then went to the class short and represented it as the number 0.0. And what he did is he treated this as a linear regression problem, right? So previously, it was a problem of predicting whether he is tall or short. Now it's a problem of predicting whether 0 or 1, right? Somebody tried this, built it, and in the end, he turned with this data set, right? Remember, this was the data set. This is X. This is the heights and widths. This is the kilograms, right? And then this is the point. It's either 0.0 or 1.0. We use this data set and then simply built this line, as you can see it here. This is called the linear regression line. It's very simple, as we did before. And then he asked himself, how can I use linear regression, which gives me this, remember? So it's A times X plus B. How can I use this to predict a class? He answered it very simply, using an if statement. If AX plus B is bigger than 0.5, then it is tall, else he is short. So this is a method that we used. Let's see. So this is the algorithm that we used to convert linear regression into a classification model, right? So here is linear regression. We add on top of linear regression a simple if statement and convert it into a classification model. This classification model is called logistic regression. And what it does classification for us. So here, nice, we have logistic regression. So what logistic regression does is adapts linear regression to perform classification instead of regression. How does it do that? It does it by adding an if statement around the output or the prediction of linear regression. Very simple, right? Now, one person would tell me that there is a small problem with this function that we used with this linear regression. Can you find the problem here? It's a very small problem, but it's not a big deal, right? This is the problem. Since we said it's linear regression, meaning all possible values are acceptable, so we still can have a value such as 1 billion, right? Or such as -16. These values are bad for us. Why? Very simply because how do we want to use logistic regression? Like clients and people who will be working with machine learning, they want to use something called as a probability. Probabilities are easier to interpret by human beings, and that's why we try to predict values that are, as we said, easier to use by human beings. So what we decided to do is interpret the results of that linear regression as a probability, just for the ease of understanding by the people who will use the model. So then we say we have values between zeros and 1. And these values are very good. They're values of normal probabilities, right? So this is good. These are all good outputs for a probability. That's good work. But then once the line continues from here and here, we start to have values bigger than 1 and values smaller than 0. This is difficult for a human being to understand. And that's why we try to change this model by applying a function on top of it. So this function is called sigmoid. That's clear. What we do is we simply map this line, as you can see it, into this function. So this is called the sigmoid function. Sigmoid function is a very simple function. It's a function between 0 and 1. And it has this S shape. So this is the sigmoid shape. And what we do is simply we treat it the same way we treated linear regression before. So if sigmoid of linear regression of x is bigger than 0.5, we say he is tall, else he is short. So this is the new model, right? This is the logistic regression model. It takes linear regression, applies some smoothing function on top of it called sigmoid, and then wraps it on a if statement. Why do we use this sigmoid function again? It's just for better interpretation of the model by the human beings. So this model is the most interpretable model that we will be seeing. Later on, we will have some lectures on interpretability and why interpretability is very important if you're going to deploy a model. And that's why logistic regression provides us with this sigmoid function, which converts linear regression from a function that takes any value on minus infinity to plus infinity into a function that gives you only values between 0 and 1, which can be interpreted as probabilities. Just so that everybody understands what this sigmoid function is, it's actually a very simple function. Sigmoid, of sigmoid.
Can I ask one question?
Yeah.
Why we drawing the below line from until 0 and we move the line to 1?
Which one? Where are you speaking?
I mean, this sigmoid function we have yes, this line
Yes.
Why we move when we reach 0 in the x.
Got you. So this is the behavior of the sigmoid function. If you look at it here, this is sigmoid. Sigmoid is the following. You give it a value and it gives you this mapping. So it's 1 divided by 1 plus exponential of minus z. So this is just a function, right? You give it any number, it maps it into this.
There is a formula, yeah?
Yeah, here's the formula. Yep. This is the formula. It's a very simple formula. Really, you don't need to understand why and how is it made like this. It really doesn't make any sense in its own, except that it satisfies two conditions. First, it's a smooth function, as you can see here, meaning it is easily differentiable, right? So easily differentiable means that the math is correct, means that we can easily calculate A and B with no problems. The second part is that its values are always between 0 and 1. And this is very important for us. Why? For interpretation of the model. The model needs to be interpreted by a human being. So we are saying he is 70%, like 70% probability he is a tall person. It's better than saying he is tall person. What is the probability? 1,000. It doesn't make sense that 1,000, right? So this is why we're using this sigmoid function. The sigmoid function is just a way of converting the output of linear regression into a probability that is humanly understandable. So we come here again. What is logistic regression? So it's a method that tries to use or adapts linear regression to build a model for classification instead of regression. How does it do that? It wraps linear regression inside a function called sigmoid that converts any value between into a value between 0 and 1, meaning it's interpreted as a probability, and that probability is wrapped inside a if statement that gives you if this probability is bigger than 0.5, we say he is a tall person. If it's smaller than 0.5, we say that he is a short person. So did you guys understand what logistic regression is? Interpreted.
Well, I'm sorry, still didn't understand why this linear regression and if statement doesn't helps us with solving that problem. And the second question is, what do you mean by saying that two lines is problem for us? Why is it a problem?
Gotcha. Okay. Let's start a small recap, right? So do you remember how we built this linear regression line?
Yes.
Nice. So what we did is we took the x, we converted the label short into 0.0, and then the label tall into 1.0, and we built linear regression, right? We trained linear regression normally, right?
Yeah.
Nice. And then when they gave this model to human beings wanted a probability, right? So wanted something that he can interpret and understand. So what we said is, these values, when you tell him that the person, he is tall, why? Because the output of linear regression is 1000, he doesn't understand that 1000, right? What does it mean? But if you tell him that the person is tall because his percentage or his probability is 0.7, this is more understandable, right?
Yeah.
You see, linear regression can take, as we said, any line in any number that we want. So here, this line continues all the way to like 1000. And in this direction, it continues all the way to -4. What does it mean for a person to be -4? It doesn't mean anything. But if we can say that the person is not -4, but the person is 0.2% or 20%, this is the chance of him being tall. This makes more sense, right? This is highly more interpretable by a human being. So this is why what we do is we wrap the output of linear regression inside a sigmoid. So we apply sigmoid on linear regression, and this gives you a probability. Did you get this?
Oh yeah, now I got more clear. Thank you.
Nice. So sigmoid always gives you values between 0 and 1, which makes it a very perfect function for us for easier interpretation of the models. This function of sigmoid is used everywhere, actually. It's not just used for logistic regression, it's everywhere inside the neural networks and all of these bigger models. It's very useful because it's, again, one, it's easily differentiable. So you see it's a very smooth function, and it has values between 0 and 1, which can be interpreted as probabilities. This is very important, the interpretation part. So again, how do we build in a logistic regression? We take sigmoid, wrap it around logistic regression. If the probability is bigger than 0.5, we say this is class tall. If it's smaller than 0.5, we say it's class short. Do you understand right now what is a logistic regression?
Yeah.
Nice. Now let's go write the summary of logistic regression in the class notes, and then we take a small break and come back for the lab. Okay?
May I ask you, please?
Yes, of course, go ahead.
We can use this logistic regression in the deep learning, yes? As
Yes.
I understand.
Yes.
When we have situation where database is has limited size.
Yes.
Okay, thank you.
So you see, this perceptron or a neuron, a neural network, multi-layer perceptron, neural network, the word neural, in reality, it's only logistic regression. So what it does is multiplication, then addition, and then an activation function, which is called sigmoid. So this is why we are focusing a lot on linear regression and logistic regression, because later on, they are the basic building blocks for neural networks. So again, what we do is we train linear regression on the data by converting label 1 to 1.0 and label 2 to 0.0, right? Second,
normalization.
yeah, this is normalization, right? This is just a representation by representing as. Nice. The second one, wrap the output of linear regression like this, then regression inside sigmoid to get values between 0 and 1 and interpret them as probabilities. Wrap it in an if statement. If prob bigger than 0.5, then we say label 1, else we say it is label 2. So these are the steps of building logistic regression. Later on in code, this, you don't need to know this. Basically, this is just for if you are going to build your own logistic regression. Later on, when you're trying to build logistic regression, you just give it the data, call a function, it does all of this work for you. Just understand what it is doing and why it's doing what it's doing. So let's copy this picture just to put it here to understand what is, yep, like that. So what is a sigmoid function? There it is. This is the formula of it. Very simple, easily differentiable function. And voila, that's it. Do you guys have any questions so far?
Yes, I have.
Yes.
How we interpret our input to label 1.1 and 0.0?
You mean here?
Yes.
You mean here, right?
Well, we have an input and we should somehow interpret it into 1.1 and
Amazing.
0.0.
So let's say the values of linear regression are the following. X equals, Y equals, this is what we got from step 1 of linear regression. Let's directly say it's 1x plus 100, right? So this is the formula that we got from linear regression. We said we wrap it inside sigmoid, and then we send it forward. So let's say I give you x equals 60 kilograms. You put it in this formula, you predict y equals 160, right? Sorry. You take this 160, you put it through the sigmoid function, sig of 160, let's say it's equal 1.9. What you have is 0.9. You have 0.9 bigger than 0.5, then this person is tall, or this person is label 1. Did you get the steps?
Yes, and that sigmoid has some coefficients, right?
Yes.
So the way of getting those coefficients, when I can see them?
The sigmoid does not have on its own coefficients. So the coefficients are still A and B of linear regression. Sigmoid takes just one value and gives it this one. Let's write it in code, right? Colab, new notebook.
In other words, sigmoid translates the input to values between 0 and 1, yeah?
Yeah, let's say define sigmoid. It takes z, just a number, and returns 1 divided by 1 plus exponential of minus z. numpy.exp, right? I think it exists. I hope so. Of minus z. Let's say print sigmoid of 6. Probably there will be an error here, but let's see. Let me try to. Can you see it better?
Yes.
Yeah.
You see this output? 0.99. Let's give it 1000. It's 1. Let's give it minus 15. It's 0.000030 something like that, right? You see?
Yeah.
Nice. So this is the sigmoid function. It's a very simple function, as you can see. You can easily code it with hand. Not a big deal. And you can say define linear regression. Also very simply like this. It takes x, return a times x plus b. Now learning a and x also. A, let's say, equals 4 for now. B equals 6. Again, as I said, these values are just a simple function that you can call. So they exist. This function already exists. So it's a function called calculate a. It's a little bit of a long function, has lots of mathematics on it, but it's simple, right? Calculate a, calculate b, and then use it directly. So these are the a and b that we give for now. Define, make decision, right? Based on probability. Return PR bigger than 0.5, right? This returns true if it's bigger than 0.5 and returns none if it's not. We defined here logistic regression very simply as the following, which takes x, return, make decision, over sigmoid of linear regression of x. Ta-da. False. Let's say it is 60. True. As we said, it's 1 plus 100. Let's run. So 60 is tall. We give him, for example, 20 kilograms. He's still tall. How is he still tall? Yes. Sorry. Let's simplify this a little bit further. 1 and 1. We want a value that is smaller than 0.5. How do we get that? 20. Okay, so B, let's make B also 0.1. And this one, 0.01. It's still true.
I think we should have something with minus and in A or B, so we can get something.
Let's try to do this. So it's 20 multiplied by 0.01. So it's 0.02 plus 0. Let's write each one, right? Let's print these values. Okay. Print linear regression of this one. And then we print sigmoid. Sorry. Over this one and see what happens. Okay. So if we give it, for example, 10, it's still true. Why so? Let's give it 20. 0.54. Okay. Yeah. Sorry. Let's say, for example, minus 20. False. Okay, gotcha. So here's what's happening. So this is the algorithm of logistic regression in simple terms, right? These A and B, they will be learned from the data, right? So we will find the best values for A and B that makes this system work easily. But the system in general is simple. We have logistic regression, which is this if statement in here, very simple if statement, wrapped around the sigmoid function, which gives you the probabilities, wrapped around this linear regression function, which tries to do the mapping between A and the classes, right? Between the X and the classes of tall and short. So 1.0 and 0.0. Is it clear enough? Do you guys understand right now what is sigmoid? How do you do the linear regression, logistic regression?
Yes.
хорошо. Now for the calculation of the linear regression values, as I said, this is a bit outside of the scope of this lecture. I'm not trying to get into more details, but if you want more details, I can just send you to this algorithm, linear regression, sklearn. So you can just come here to this one, and basically this is the what I said, the function that you can train. So you call linear regression .fit on the x and y, and this will give you the following values, right? The coefficients, which are the a and b, right? So once you use this object and train it on the x and y, you will have your coefficients. Here they are. So this is the a and this is the b. So later on in the training, what you can do is replace this like that. This part will be like this one. Sorry. A and b equals linear regression dot fit over x and y dot coef data. There you go. This is logistic regression written in a couple of lines of code.
I'm sorry,
Yes?
can I ask a question? I
Yes.
still don't understand where our conditions where a person is tall and short, because
Yes.
now it's only if negative value it's short and if positive value is tall, but it doesn't make sense.
Yes. This is because of the A and B, right? So this depends on the A and B. Depending on where you put your A and B, this negative and positive will change, right? So if I had, let's put a good example here. So what we are trying to do is AT becomes 1.0 and 60 becomes 0.0, right? How can we do that? Let's write it here. Y equals how much? Okay, let's say 0.01 times x minus 0.5 or 0.6 minus 0.7. Хорошо. A equals 0.01, B equals minus 0.7. A person with height 20, a person with height 20 is false, which is short, or let's do it here, right? If PR bigger than 0.5, return tall, else return short. Here's the if state. Short. Let's say he is 50. 50 kilograms. He's still short. Let's say he is now 80 kilograms. He is tall. You see?
Yeah, great. Now it's more clear. Thank you.
Yeah, it all depends on the values of A and B. Of course, the values of A and B are the learning you are doing. This is the model you are building, the values of A and B. So the learning of these values happens by reducing that error that we were speaking about, the minimum, what is it called? The squared error. Remember, the sum of squared errors, right? So we're trying to minimize the sum of squared errors over the A and B. And this happens using some simple derivations. If you come here to this function on theta, there you go. It's a function of X and Y. And what it does is simple. This is just some checks. Processes the data, rescales the data. This is useless. Optimizer here. So this is bad for us. Yeah, I really hate this. Nah. So the code is inside this optimizer. Well, that's bad for us. But we can try. Where is this optimize? Okay, so it's scipy.optimize. We go to this scipy. Duck. Minimize. I want to see the code source. A lot of documentation, but very simple code. Let's just say linear regression closed form solution. Here it is. So this is the final result. So W is the vector of coefficients, and it's equal to the following. So it's the sum over I of xi multiplied by yi divided by the sum over xi squared. So again, this is just the derivation of what?
Squared error.
Nice. So this is the derivation of our squared error. After there is a lots of steps here that are ignored. After we finish the derivations, we get a simple formula for every single one of these A and B. And that's it. That's the learning. Хорошо?
Yeah.
Yes.
Nice. So I hope that you are already familiar a little bit with what linear regression is. You start to understand what is this intelligence in reality. So what is this machine learning, how the learning is happening, all of these things you're getting more ideas or more top terminology from these subjects. We'll take a small 10 minutes break and then we start our lab. In the lab, hopefully you will get even better understanding of these concepts. And on the next week, definitely you will at least understand all the concepts related to neural networks, computer vision, and what is it called? Convolutional neural networks, and all of these concepts. Hopefully we will cover them in the next lecture. Once we finish from this, we'll start speaking about what we will do in the rest of the semester, right?
Excuse me, what we should prepare for our lab?
For what?
For our lab, what we should prepare?
Just nothing, just relax and spend 10 minutes, like, what is it called? Just breathe, eat some stuff, and come back in 10 minutes, right? And we will do the lab together. No preparations needed.
Okay, thank you.
You're welcome. Thank you. Sure. Stop the recording. You're recording, right? Nice. So basically what you will be doing, you will go back home and see these results, see something similar to this code, but it will have some bugs in it. Try to fix that code, and this will be like one way of training, right?
Oh, okay.
Now, data transformations. This is very important. Before you send your data to any model or to any machine learning model, usually you will be applying different types of augmentations or transformations on the data. These transformations are the following. So dropping user-specific columns, such as the name. Another column could be like social security numbers. All of these columns that can link back to the private information of the person. What we do is we drop them directly. Okay. Did you get why should we drop the name and all of this sensitive information?
Because it's like a predicted column, no?
No, the name, for example, it's first of all, the name is not going to help you understand anything about the person, right? So if I tell you this person's name is Mikhail or this person's name is Andrei, you really can't use this information to tell me he lived or he died. So this is kind of useless information for the model. Another point is that this information is private for the person. So usually there are some heavy regulations on what type of data you can use for training and what type of data you cannot use. So in this case, name is something that you should not be using for training. Did you get it?
Yeah, it's
Nice.
useless information.
Got you. So here you can see this is the data set and it has the column name in it. After we did this data drop name, our data set becomes the following. The same, but without the name column, right? Nice. Another function that is very important in Pandas is null. So this function dot is null is very important because what it does, it goes through all the values of your data set and tells you if you have that information or not. So for many reasons, so you can see here, we have this value, we have this value, we have this value, we have this value, but this value, we do not have it, you see? Why don't we have this information? Mainly because when, for example, because the Titanic sank and we don't have all the possible information about every single passenger in the, what is he called? In this, in the Titanic, right? So for some reasons, some information can be missing in your data. And you can easily test for that using the dot is null operation, right? So this gives you the following. And you can summarize this information on the table by using the dot any function. So dot any function, what it does is it goes through every single column and tells you if there is any information missing in that column. So for example, passenger ID or passenger class, we always have the information of the passenger class for all the different passengers. So dot any gives you false. But for example, the age, you see, we have this, all of these, we have them, but this one, we do not have it. So dot any returns that age contains missing information. On the other examples, for example, here we have the fare, the cabin, the embarked, boat, body, and the destination, right? So all of these variables can be missing in most cases. So for example, the home destination, let's say that this passenger was trying to go to New York, the other passenger was trying to get to Washington, but this information for some passengers, we don't know it, right? So the passenger died already. Like you can't ask him, where were you trying to go on the Titanic, right? So this is why some of the home destinations are missing. So this is the importance of the is null dot any function calls. To understand here are the different counts or the different, let's say, percentages of whether we have the information or we don't have it. So in this case, you can see that which ones are the most? Ta-da, tuck. Mhm. Here. So here we have age. In most cases, we don't have it. We have boat. We kind of have it on most cases. Body, we have it. Cabin, we have 77% of it. Embarked, we only have 15% of this, the information. Fare, for example, we only have 0.08 for it. Home destination is, we only have 43.09% of it. So this is useful for you to understand which information, which variable should you keep or which variable should you delete, right? So for example, if I tell you that most of the passengers, we don't have this information about them. So it will be kind of useless to use fare as part of your training information, right? So in most cases, fare, you will be dropping it out of your data set. Embarked also, you will be dropping it out of your data set. Many people take this age thingy and also drop it. They also drop home destination. All of these variables which have a lot of missing, what are they called? A lot of missing, help me out. A lot of missing values, we shouldn't keep them, okay? Because they do not provide enough information about the instance. Now for the values that we can keep or we want to keep, we do the following. So there's this simple imputer function from sklearn. What it does is it takes the missing values and using some strategy, we will be imputing these missing values. So let's come here, for example, and see this following, the following part. Tuck, 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 tuck. Let's say this is nan, right? Cabin is usually a character, like a string, like this. Can you give me an idea on how to fill these not a number, these missing values? How can we fill them? Can we find a strategy? What should we put as values in these places?
Maybe they work on the bullet.
The what?
Empty string, maybe.
An empty string, nice, to represent that it is missing.
Most frequent value.
Aha, that's much better. That's a much better information. We use the most frequent value and use that to put it in all the different not a number or missing areas. Now let's go, for example, for age, right? Let's say for some of the passengers, we don't have the age. What can we do about that?
Take the medium, not
Take
medium.
the mean,
Average.
for example, or the average.
Mean age.
We can take the median, right?
Maybe
Nice.
medium.
So there are different types of imputation values. So in this case, our strategy is called median. What is median? If you're not familiar with median, so it's this. Let's look at it. There it is. So you see 1, 2, 3, 1, 2, 4, 8, and 15. The median is the value, if you order your data, it's the value that is exactly in the middle. So if you calculate the mean, so it will be like 15 plus 8 plus 4 plus 2 plus 1 divided by 5, right? This is the mean. The median it's not calculated like that. It's much simpler. Simply the median is the following. We order our data set and then we take the value in the middle. Ta-da, you see? Here we have the sum, division. Here it is, 5. In this case, we just go through ordering the data and then find the value in the middle. If the value in the middle doesn't exist, we take this the average of these two values in the middle. Do you understand what the median is?
Yes.
Yeah.
Yeah.
Nice. So basically what we will be doing is we will go through the data. Whenever we find a missing value, we will put the median of that column in that value. Another method on this embarked, for example, what we will do is we will use this strategy called most frequent. What is most frequent? As you described before, since we are using a string, We cannot say the average of the string, or we cannot say something like the median of the strings, but we can say the string that is mostly repeated, right? So basically the most frequent value. This is our method for imputing the data, right? Хорошо?
Отлично.
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 Nice. Now for the others, we usually would just drop the rest of the columns which we do not impute. We drop them because they have lots of missing information. And now we have the following. There you go. So this is our new data set. Another technique that is very important for you guys to remember. So what we have seen so far is dropping user ID columns and dropping columns with lots of missing values, and imputing these missing values, if we have enough, by either the median, the mean, or the most frequent value. Now, the second two types of preprocessing or data transformations are called encoding, right? After that, we will speak about normalization. So first we speak about label encoding, and then about one-hot encoding. Ta-da! Nice. Do you guys know the difference between ordinal and nominal variables, categorical variables? This is in statistics.
Yeah, the scaling, I think, yeah, you mean
Nice.
ordering.
Exactly. So basically, categorical values, which have only classes, right? So basically, this is a dog, this is a cat, this is a cow. We have the following nominal categorical values like this: cow, dog, cat. There is no order between these objects, right? They're just like that. Another type would be the ordinal type. Ordinal, such as for your grades, right? So there is A, which is better than B, and then B, which is better than C, and then C is better than D, right? So you have this order between the categories. Okay?
Yeah.
Nice. So basically, there is this small difference between nominal categorical values and ordinal categorical values. And we speak about this difference because it's important for the preprocessing. Label encoding is done on what we call as ordinal data. So let's say, again, with the grades, we have A, B, C, and D. Remember linear regression. The input for linear regression is always a number, right? Remember, so it's y equals ax plus b. X must be a number. You can't put a string in place of x, right?
Yes.
This problem happens in all of the machine learning models. Usually they only require you to put as input a number, not as string. So what we do is we have to convert all the strings that we have into a number. So if the strings that we have are ordinal, as we just said, that means we can do the following. Convert A, for example, to 1.0. Sorry, convert B into 2.0, convert C into 3.0, and then convert D into 4.0. So this is called encoding, right? We give a code to these strings. When the strings are ordinal, when the strings are, sorry. Okay, when the strings are ordinal, the numbers that we give should have an order, right? So the same order of the strings will be kept in the order of the number representations that we give. If, on the other hand, we don't have any, sorry, like this, so we don't have any order, let's say cat, dog, mouse, and horse. We don't have any order in these three, right?
Oh, what's about the height?
Yes,
or
weight. We can do that, but now you are not encoding the cat. You are encoding the cat's height. You see?
But in previous example, you enumerate your letters A, B, C, D. How
Yes.
to understand that A is better than B or C, and etc.
Exactly. The concept A is better than the concept B. But in this case, the concept cat is not better than the concept dog.
But it's smaller.
It is smaller, yes. So if you want to encode this information of height, then you keep it. But let's say the cat is smaller than the dog, right? But the cat, let's say, is, I don't know. It's better than the dog in other stuff. I don't know where the cat's good at. Let's say, yeah, dog is smaller than a horse, but the dog is more useful than a horse, right? So dog can be used for surveillance, but the horse cannot be used for surveillance. If you put this order between dog and horse, you are forcing the model to say that dog is better than a horse. If this is what you want, if this is what you need for your model, then yes, use label encoding as before and say, for example, this is 1.0, this is 2.0, and this is 3.0, if the order is important for you.
Okay, it depends on the task.
Exactly, depends on the task. But in the case of general work, you're trying to represent the concept cat without forcing any order between these concepts. What you do is simple. You create a vector. You know what is a vector? An array with the same length as the number of classes here. This technique is called one-hot encoding. Meaning inside this vector, we have only one value set to 1. All the other values are set to 0. So whenever you have a cat, you represent it as this vector 1, 0, 0, 0. Whenever you have a dog, you represent it as the vector 0, 1, 0, 0. Whenever you have a mouse, you represent it as the vector 0, 0, 1, 0. Sorry. Okay, so this is what we call one-hot encoding. Did you guys get it?
At what maximum quantity we can use this approach?
That depends on you. Say you have 100 categories, right? Will you make a vector of 100? This is too big. Some cases it's too big. In some cases it's not too big. There are cases, for example, let's speak about this one, ImageNet. ImageNet is a competition that's been like between big companies such as Google and Facebook. And here they represent 1,000 concepts in a vector of 1,000. For them, it's not big, but for you, if you're going to train it at your home, on your laptop, it's going to be too big. You see? So this idea works with anything you want, as long as you can afford to use it. It's very difficult and it's very time consuming in time and in calculations. But if you can do it, then do it. Okay. Does that answer your question?
Yes.
хорошо. Now, this technique, we will apply it to this embarked. So in embarked, we have three categories. I have no idea what embarked means, but let's check it here. Probably it has like some, yeah, embarked, port of embarkation. Okay, so there are three locations where you can enter the Titanic from. So there is this Cherbourg, there's Queenstown, and there is Southampton, right? So these are three places where you can enter to the Titanic. These three places are three categories. You cannot say that Cherbourg is better than Queenstown or Southampton is better than Queenstown, right? So this is why we are considering these thingies as a nominal category, right? And we are encoding them like this. You see this vector? 0, 0, 1. You see? 0, 0, 1 means that they were embarked on Southampton. If I wanted to say that they were embarked in Queenstown, what will be the representation for Queenstown?
0, 1, 0.
Exactly. This would mean that they were embarked on Queenstown. If I want to say that they were embarked on this sea,
1, 0, 0.
exactly, that's it. This is what one hot encoding is, right? It's very simple. It's one method to convert this string into a number that the model can learn from. Okay? Nice?
Yes, sure.
хорошо. So far we spoke about dropping the user IDs and the IDs with lots of missing values. We spoke about imputing the missing values using either the mean, median, or the most frequent value. And we spoke about the two methods of encoding, which is label encoding and one-hot encoding, right? Depending on this categorical versus nominal, so categorical nominal versus categorical ordinal. Now we will speak about this normalization. Now for normalization, remember the problem we had earlier in here? Can you see this screen that I'm showing?
Yes.
Yes.
The one where we are speaking about NumPy and like this. Can you see it?
Yes.
Remember when one of your friends said, it's not working very well with so if it's positive, it's true. If it's negative, it's false, right?
Yeah.
He's right. This is a problem because it gets difficult to understand when you are working with large numbers. Because when you're working with a number that is not limited, you don't understand what is big and what is small. So for example, if I tell you the number 10,000, is it big or is it small?
Depends.
It depends, exactly. If you're speaking about, if I'm like working with only numbers in 0 to 1, and then I speak about the number 10,000, number 10,000 becomes very big. But if I'm speaking about like distances between different planets, which is like, I don't know, like billions of billions, and then I speak about just like the differences between like two countries, which is like 10,000, 10,000 becomes a very small number. So this idea of having a value that is not limited becomes difficult to interpret, right? But if I tell you that all my numbers are between 0 and 1, and they are distributed normally, 0.9, is it big or small?
Big.
0.001, is it big or small?
Small.
Exactly. So when you kind of limit the values that you have between 0 and 1, you get this better understanding of what the value means, right? And this is why we apply this thing called as normalization. So normalization usually happens either between 0 and 1. We normalize the values to be between 0 and 1, or we normalize the values to be between -0 and 1, right? So there are two methods. You can choose whatever you want. Mostly neural networks can work with both of these methods, so you can try the one that looks easier for you. Sure. Page.
Well, the function that described us in your example below, data point describe.
Where is it? This one?
Yep.
Yes, what is it?
What is doing this function?
Who is doing this function? This function is inside pandas.
No, I mean, what this function does.
It calculates these values. It calculates the number of values you have. It calculates the mean of the values. It calculates the standard deviation of the different variables, the minimum value of the different variables, the maximum of the different variables, and this. These are the quantiles.
Okay, thank you.
Хорошо? So it just basically describes your data, right? Nice. So how do we do that? Again, there are different techniques for normalization. This is one function for normalization. So we take a value minus the smallest value in the data set divided by the maximum value in the data set. So we have the following, right? Say you have -5, 1, 3, and 1000. And you're trying to make these values all between 0 and 1. So what you do is take -5, take every value minus the minimum value divided by the maximum. So let's say -5 minus -5. How much is that?
0.
-5 minus -5, it's 0, right? 0
yeah.
divided by 1000, how much is that?
0.
0. So this value becomes 0. 1 minus -5, how much is that?
-4.
No, it's 6.
6.
So it's 1 minus -5.
Minus, sorry.
Yes.
Okay.
So it's 6 divided by 1000, it becomes 0.006. For 3, it becomes 0.008. For 1000, let's do 1000 minus 0.5. Sorry, 1000 minus -5. How much is that?
1005.
1005. 1005 divided by 1000.
0.005.
1.005. Right?
1.005.
So this is one method that takes large values and converts them into something between 0 and 1. In this case, why we have something bigger than 1, it's mainly because when we calculate the maximum, we shouldn't be using the data as it is. So we should use df minus min. Okay. So basically for the calculation of the maximum, we shouldn't take 1000, we should take 1005. But this is like a small change, right? Very basic change between different formulas. And there you go. This is one method that converts numbers in random range into numbers between 0 and 1. Okay. And then we have this age which becomes the following, right? So previously age was like 40, like in here, 29 years old. Now it becomes 0.36. You see? You got it?
Yeah.
хорошо. I don't think we can finish this part, but let's try, right? Another very important thingy that we need to understand. So two concepts, the concept of dependent and independent variable, and the concept of train, test, and valid. So what are the dependent variables and what are the independent variables? I think this, it's a little bit too much. Let's remove this part also. Let's also only speak about the train, test, validation, and then speak about the dependent and independent variables a bit later on, okay?
Okay.
хорошо. So why do we do this train, test, validation splits? The process of training your model is the following. First, you train the model. Second, you test the model. If it is good, 3, you deploy the model. Now, this was the process previously. So basically what we should do, we have a training data set and we have a separate testing data set that we don't touch during the training. We just use it to evaluate if the model is good or not. If it is good, we deploy it. If it's not good, then we go back to the training. Okay? So far sounds logical, right?
Yes.
Now let's imagine a small scenario where you train a model, test it, and find that it is bad. You go back to training, you test it, find it's bad, training, test it, find it's bad, training, test it, find it's bad, training, test it, find it's bad, train it, test it, finding it's bad. You keep on repeating this a lot and a lot until you get a model that gives very good results on the testing data. Is this a model you can trust or a model you cannot trust? So basically,
we need to check.
Yeah, how do you check if a model works or not? When you test it on a data that he has never seen before. But when you do this train, test, train, test, train, test, train, test, train, test, train, test, the training of your model kind of becomes dependent on the testing data, right? So what you're trying to do is trying to change the parameters of your model in order to pass some threshold on the testing data. So this testing data, your model has seen it so many times that now it's not a good evaluation of your model. Okay. So basically repeating this training, testing, training and testing, training and testing too many times kind of takes away the trust that you give to the evaluation in here. You cannot really trust it that much if you keep on repeating it too many times. This is why they introduced another data set. It's called the validation data. Validation data is used to temporarily test or evaluate the model. So what you do is you take a small part from the training data. You do not train on it. You only use it for testing. Okay. So basically, you train the model, find that the model is bad, go back to train the model. Find the model is bad, you go back to train the model. Find the model is bad, you go back to train the model. But you are only working on this data set, right? So it's the validation data. Once you pass on the validation data, you go to the testing of the model. So this means that the test data, we only use it once, right? We just see it, or the model, our model sees the testing data only for the first time. This is not some question that has been repeated on the, so for example, these are the test questions and these are the quiz questions. If I always give you like the same questions for the test and tell you the results, give you the same test every day, and you go back and come to pass the test again, the accuracy or the trust that I give to that test is not very high. But if on the other hand, I give you this quiz, right? It's a small test, just a quiz where you can train on it. Go back and do this iterative process again and again and again. And then with your test, you only do it once. This gives more trust or gives more importance to your evaluation, makes your evaluation more accurate. Okay? And this is the reason why we always split our data on 3 data sets, right? We have the training data set, which will be used for training the model. We have the validation data set, which will be used to temporarily evaluate the model. And we have the testing data set, which will be used at the final step of evaluation. In most cases, what happens is the following. You give to the data scientist only the training and validation data. And for example, the test data is hidden in another place where the data scientists don't even look at it. They don't even know that it exists. After they finish their training, you test it on the test data. After they finish everything they have, you evaluate it once on the test data. Because having a very good evaluation is key when you are working in the industry, when you're trying to like deploy something for clients, okay?
Do you have an example of this data splitting?
Yes. I will give you an example of something we worked on Provectus. Provectus AI Foundation. Dun, 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 dun. No. So this is the company that I was working on previously, and this is the project that we worked on. So what it does, it's a computer vision project, and it tries to predict. Let's not look at this. Let's look at this one better. Yeah, it's the same thing, but it doesn't have anything also. Let's see. Let's just read it like this. So basically, the goal of this project is to detect face masks on human beings, right? So basically, me personally, I built the face detector. What I do, I need to like find the best face detector. So what I did, I took a small part of my data and I train and evaluate it on that small data set. If the results are good, I send them to my supervisor. My supervisor has a testing data set. He doesn't show it to me. All he does, he uses my model on the testing data set and tells me if the model is good or not. Okay?
And it was difficult to work on this test data set?
Yes, it was very difficult. Yeah, of course. Mainly because the testing that we used was from a data set from the US, and the training data that we used was from China. There were lots of problems there. But yeah, it was very difficult.
You trained your... Okay, sorry.
Just you need to understand something. Data splitting is something very important. Why do we do it? We do it so that we can evaluate our model very accurately. So basically, we have something called as the training data, and then we create something called as the validation data, where we temporarily train our temporarily test our model on it. And then we have the what is it called? The test data, where is the final evaluation of your model that goes before the deployment. Okay.
I'm sorry, can I ask please?
Yeah, go ahead.
So in a Titanic dataset,
Yes.
we will split our data by 2 and try to check it with the rest, with the second part, right?
Yes. So here we have this function. It's called train test split. What it does, you give it a data set. This is the X and Y, and it splits it according to what you say here. So for example, this is the test size, 0.2 or 20% of the data goes to the testing. 80% of the data goes to the training. And here it is. X train, X test, Y train, Y test. We give it this and this. So previously we had 1,309 samples in the whole data set. Now how many do we have in the training? 1,047. How many do I have in the testing? 262. Okay. Now one person would say, but where is the validation data, right? Can somebody answer me where is the validation data in this work?
Maybe there is no validation data.
Nope, there is a validation data. There is no testing data. Remember what I said? The testing data, you don't have access to it at all when you are doing the training, right? So basically what's happening here is this data that I call test, in reality, it's the validation data. This is the validation data. And the test data, if you come to Titanic, you will see, here it is. We only use this train.csv data, right? The test data is in a completely separate file that you do not use at all until you finish your work. Did you see it?
How to understand that you finished your work?
Yeah, basically you just say that I have the model, I trained the model, it's finished, and then you give it to like to your supervisor or to the person who will be using it.
But here I must understand that your training and your data is good, yes?
Yes.
And how does he understand it?
Yeah, basically what he does is he have this testing data set in here, you see? What you have access to in here, you will not see survived, right? You will not find it in here. So what happens is you make this submit predictions, you upload the predictions in here, and the Kaggle will calculate your results for you. So basically Kaggle will tell you your accuracy is 98%. You see? In real life, if you're going to work in a company, basically Kaggle is your supervisor and he will tell you accuracy is 87% and you should repeat the training. Did you get it?
Before you start your training, we have 20% of data and we go to the Kaggle to get validation data for your supervisor, and after that you will test your other part, 80% of data, and if your data is okay and validate with the data from your supervisor, it's done. Yes.
Yes, you can think so. You can think of it like that. So basically what we have is like this. Sorry. We have a training data set. We split this training data set into.
But your algorithm should be similar.
Yes,
with,
yes. One second.
For example, Kaggle and your.
This is the data set, right? This is the testing data set. So this part, right? Let me do it like this. So this is the testing data set. We don't have access to it, right? We don't use it. This is in Kaggle, right?
Okay.
This is the training data that Kaggle gives you. All of this, sorry. All of this is what Kaggle gives you to do the training. Now, what you should do is simple. You come here, split it in like this. This is the validation data. And this is the training data. So what you do, use this. Sorry. Use this
Why?
for
Mhm.
training. Sorry.
Why blue line is validation data?
Yes. Use this blue data for personal validation,
Oh, okay.
for a personal evaluation. This data is used by your supervisor to verify your results, to show that you didn't cheat and your model works well. Okay?
I understand the approach, but I don't understand how the Kaggle and your algorithm should be to get the similar data at the end of your work. Okay, thank you.
This is like something else. This is like specific for Kaggle, right? But what you will be working on is something that you will be doing the splitting, right? So basically, in real life, you will have this data, right? Full data access, and you should call this TTS on your data. It gives you train and test. And then what you do is you take this test data, hide it somewhere else, and create the test train valid from the training data. Okay.
I'm sorry, how does it split it randomly?
Yeah, randomly.
Oh, okay.
Yep. Just randomly, this one goes here, this one goes there.
Okay, thank you.
You're welcome. So basically, what we have spoken about in, sorry, let me share the screen again. Nice. So what we saw in today's lab, we spoke about how to read data, how to visualize some data. We spoke about different data transformation techniques, and we spoke about the importance of splitting your data between training and testing, right? Are you guys all familiar with Colab?
No.
Nice. So now I want you guys all to go to Colab, create your own Colab link, Colab notebook, and come to this website. And basically copy paste this code to Colab.
Could you give a link to Colab, please?
Yes. And now I want you guys to explain to me what's happening in this code. So it's like the reverse of what I just did. I explained to you that code. Now you guys should come here, execute this code, and explain it to me. Okay?
Could we use another idea to launch
run it.
this code? Yep.
Yeah, of course, you can use anything you want.
Okay.
Yeah.
This code printed only one coefficient. Is it correct? Ah, yes, it's correct. Understood.
Mhm. So go ahead, explain to me, guys.
I can try.
Yeah, go ahead, go ahead. Yeah.
Firstly, we download data sets, dropping other columns for using only one column as a feature.
Mm-hmm.
Splitting data set on the test with only 20 rows.
Mm-hmm.
Data targets initialize the objects, feed the data, then propose graphics and squares.
Nice. So where is the training happening?
During the calling the fit method.
Nice. Where is the evaluation happening?
Predict method.
Nice. Now, let me ask you a small question. Can you change this code and make it use this? Instead. Go ahead. Just do it locally and tell me what the output is. Hmm. Can somebody explain to me why is this Reger coef gives only one value?
It's constant value of the coefficient.
Mm-hmm. Ta-ta. Somebody needs to go and read the documentation, right? Mm-hmm. It's the same number here. So that means we're good, right? What is missing, guys? You see? So this coef gives you the A. Intercept gives you the B. Makes sense now?
Intercept is what?
The B. Remember, it's y equals A times X plus B. This is A. This is B. This is the intercept. This is the coefficients. Okay? Uh-huh.
Yeah, but when we use that values, then
Which values?
that A and B.
Let's use it now. Print. At 0. So the first coefficient times, let's give it an X. Give me some X, guys. 0.10, right? Plus the intercept. Here we go. This is your linear regression. We come here. We said 0.10. Go up. There you go. Let's do it with lines, right? We said 0.10. We go up. It's kind of here. Ta-da. You see? You just did your linear regression. Did you see how to use these values?
Yeah.
Yes.
Nice. So this is again how linear regression is done, and most of the machine learning algorithms will be working. So simply, you call the algorithm and you call its fit function on the training data. That's it. Doesn't really require a lot of work on it. Okay?
Yeah.
хорошо. So for the purpose of the next project, the first project, what I will be asking you guys to do, so it's not for this week, it's for next week. What I will ask you next week to do is to build variable or different machine learning algorithms on a simple training data set. And just give me the different metrics, right? Accuracy, precision, and all of these things, okay? хорошо?
Yeah. Do you have the detailed explanation of the
Not
task?
yet, not yet. Next week, I will give you the task, guys.
Okay.
Do you guys have any questions for now?
No.
Nice. If you don't have any questions, then let's come and finish writing our class notes for the lab part, right? What did we learn in today's lab?
Let's read in your description,
Yes,
in your document.
but I want you guys to write it, right? So we learned about data reading, data visualization, and data transformation. So this is the most important part that I want you guys to write about. So start speaking about the data transformations. I will look on the document from this laptop. Go ahead. So tell me what you learned about the data transformations.
Dropping the useless maybe columns.
Nice, nice. Yeah, write them all. What do we do with missing values? Nice. Nice. And can somebody start writing about encoding, right? Label encoding and one-hot encoding. Let's see how much time is left. Oh, we already finished 10 minutes ago, didn't we? Let's finish writing about like the encoding and we call it a day. Nice. Nice. Very nice. Nice. Let's call this final evaluation. Nice. Yep, exactly. Okay. Nice. Nice. Normalization, very well. Nice. And label encoding, we use it on which type of data? Sorry. Let me just maybe copy paste this image. It will be useful later on.
Could you describe, please, what will we get in our homework? For example.
What do you mean? In the homework, basically, you will have a simple task of training different machine learning models on a simple data set.
It will be the part of the maybe some project, or it will be separated homeworks.
No, it will be part of the project, right? Remember, I will give you 2 weeks for the project. Next week, I will give you the project. And basically, you will split yourselves into groups of 2 or 3. And every person will try to do, well, basically split the task between you guys, right? I will give you a very, like, what is it called? Detailed description of the homework task. No worry.
Thank you.
Thank you. So nice. Now, I highly encourage you guys to continue working on this lecture notes. Maybe clean them up a little bit, make them a little bit more beautiful. And later on, for revision, for preparations, for the quizzes, you should use these lecture notes, because most of the questions I will be asking, will come from this file that we just wrote together. Okay.
Okay.
Yeah.
Хорошо. Thank you guys so much. I will upload the recording to the Moodle, and I will upload the lecture slides and the different links that we have used today also on Moodle. So thank you, and see you next week.
Thank you.
See you.
Thank you.
Goodbye.
Goodbye.
Bye-bye.
Bye.
Thank you. Bye-bye. Mm-hmm.